Let's discuss the basic process of analyzing capacitor circuits. These are defined as circuits with just capacitors and nothing else in them. Later on, we'll study more complicated circuits with capacitors, resistors together, and resistors and inductors together, or capacitors and inductors together. But right now, it's just a pure capacitance circuit. Now, in practice, I would not advise you to make a circuit like this because the capacitors will immediately explode. You have to put some current limiting resistor in series with the battery or with one of the capacitors actually, in order for them to charge in a gentle fashion. So all of these capacitors should have resistors in series with them in real life applications. Now, when I draw a circuit like this, you should assume that this 18-volt battery has got several 1.5-volt batteries that join up to make 18 volts. So that's why it's called a battery. Otherwise, it would be called a cell. The cell is an atom, and the battery is a collection of those cellular atoms. Okay, so that's terminology. The other thing is that we're going to assume that these wires have no intrinsic resistance, so everything is pure and ideal. Let's, for the sake of analysis, take the capacitors to have some capacitance. Let's say the ith capacitor has got a capacitance of I microfarads, which means that this has got 1 microfarad, that has got 2 microfarads, and that has got 3 microfarads. Okay, I equals 1, 2, and 3. So that's going to be the basic problem I'm going to analyze. And what do I need to find? Basically everything. So find the charge on each capacitor, and I'll indicate the charge. Because I have this microfarad, charge is going to be in microcoulombs. So anytime I draw a circle, I'm drawing microcoulombs. The voltage is 18 volts, so all the voltages will be in volts also. So I'll put triangular symbol is voltage. Then I have to have a symbol for the total energy in each capacitor. For that, I will put a square symbol, and anytime I put a square symbol, the units for that are in microjoules. And the capacitor itself is a parallel plate capacitor. So when I put a parallel plate capacitor with a value between the plates, that value is automatically in microfarads. So that's the basic scheme, diagrammatic scheme I'm going to be using. Now, let's look at the formula for energy. There are several formulas for energy, but the one I'm most fond of and I'm going to use quite a bit in this analysis is 1/2 QV. And if you look at my notation, that's 1/2 a circle times a triangle. So whenever we see a circle and a triangle, we just multiply them and divide by 2 to get the total energy. Now, the first step in the analysis of this problem, you can actually analyze it with this diagram itself, but I'll teach you a foolproof method known as the tree diagram analysis. So first thing is to make this into a tree diagram. So I take the 18 volts and put it right on top. Now it's going to branch out at this point. I'll indicate that here. The left branch is going to have C1 and C2. So that's going to be 1 and 2 between the plates. Remember, when I put 1 and 2 between the plates, I'm referring to 1 microfarad and 2 microfarads. And then the right branch has got 3 microfarads. And then those things will come and join up again, that I'll indicate here. And after joining up again, they'll be sent to the negative terminal, which in our language is the ground. So in this manner, I've converted the original circuit diagram into a tree diagram. Now, the philosophy of this method is to prune the tree at each step and keep reducing the number of capacitors. So the first level of pruning will be to add these two capacitors in series. Now, capacitors in series, off to the side, I'll tell you how they add. In an earlier video, we saw that capacitors in series add like this, C1, C2 over C1 plus C2, and we're only ever going to do 2 at a time. And capacitors in parallel are just going to be C1 plus C2. Because we only do 2 at a time, these two formulas are sufficient for all analysis. And there's a reason not to do only a two at a time, and that's because when you hop back in the sequence of this unpruned trees, you will get all the values one by one. So it's essential that you not do the entire problem at once. Don't be a hero and condense everything into one capacitor in one step. It serves no purpose at all. So the next step, because I'm combining these two in series, the total capacitance is going to be 1 times 2 divided by 1 plus 2, or 2/3. That I'm going to leave alone. And you can already see the tree is pruned. It's becoming smaller. Okay, now there's only one more step. I chose a simple problem for illustrative purposes. In your homework, you're going to have more than 3 capacitors, maybe even 5 or 6 capacitors. So you may have to prune this in 5 or 6 stages. But 3-stage pruning is all I'm doing here. And the last thing is 2/3 and 3 in parallel. Well, they're just going to add 2/3 plus 3. 3 can be written as 9/3. So 9/3 plus 2/3 is 11/3. And in this way, I have found the effective capacitance. If I want to replace this entire problem with a single capacitor, I have done it here. This is called the effective capacitance, C effective. Now we are also required to find everything else, all the voltages, all the charges, and all the energies. Okay, so once you have, let me label these trees by Roman numerals first. I'll call this Roman numeral 1, Roman numeral 2, and Roman numeral 3. Now what we're going to do is we're going to reverse hop. We're going to, each time we hop back, we'll fill in more details. So from this completely pruned picture, that's like the Charlie Brown Christmas tree with just one ornament. Now what we can do is we can find I'll analyze the third Roman numeral. So I get from the basic equation, remember, capacitance equals charge by voltage. And that means charge is equal to the effective capacitance times the voltage. That tells you the entire charge in that final capacitor. So we can evaluate this. Let's do that. This is 11/3 microfarads. And the voltage is 18 volts. Well, 3 6 are 18, so that's going to be 66. Microcoulombs. Well, that's nice. So what I'll do is I'll immediately put my 66 here. Okay. What else can I do? Well, I guess I can find the energy because I have a circle and a triangle. So 1/2 circle times triangle is the energy. So let's find that. The net energy in this entire electrical potential energy in this entire circuit can also be got by the final pruning of the tree. So that's 1/2 circle times triangle. So that's 1/2 66 mu C times 18 volts. Well, that's 2 9s are 18, and 66 times 9 is 594. I'm not trying to impress you. I worked these numbers beforehand. So that's 594 mu J. I can put that here because my symbol for total energy stored is a square box. Now let me hop back. I found everything I can find about this. Let me hop back. Now the one thing you know about parallel combinations is that they have the same voltage across them, which means that the voltage across this and the voltage across that are going to be the same. What I'll do is I'll put a triangle like that. I mean, I can shoot ahead and do this here also. But here I've got to be careful. I don't know how to split the voltages yet, so hold off on that. It's okay to go back as far as you feel comfortable, but then don't let's not get cocky and do everything at once. So now we'll just figure out what the charge is going to be. So now I'm working with Roman numeral 2. So here I can find the net charge Q3 by the equation. It's C3 times V3. Well, the capacitance is 3 microfarads and the voltage is still 18 volts. So that's 18 threes are 54 microcoulombs. Now once you have the charge on one of them, you can find the charge on the other one by simple subtraction, because 66 has to be equal to 54 plus what remains, since charge is conserved. So by that charge conservation principle, I can fill out both these entries. 54 plus 12 is in fact 66. If I wanted to, I can go and put the boxes here, but it's not worth it. So in the intermediate stages, I will not do the energy boxes. I'm just going to do the energy boxes in the last stage and the first stage to save time, and who really cares about how much energy 2/3 stores? It's not even a real capacitor. So what I'll do is I'll hop back at this point. Now 18 has already been assigned. Once I have 18, I can assign the also the charge is not going to change from here to here. So I'll put that also here. Okay. Now once I have up to here, all I have to do now is to figure out a way of splitting these voltages. Now if it was 1 and 1, by symmetry you could have given this half and that half. Unfortunately, that's not the case. It's 1 and 2. So you have to use the equations to decide. So let's go to analyzing Roman numeral 1. By the same equation, C equals Q over V, we get V equals Q over C. In other words, V1 equals Q1 over C1. So let's find the voltage across the capacitor, 1 microfarad capacitor. That's going to be 12 mu C divided by 1 mu F. The mu's cancel out and I get 12 volts. Well, that's nice. Once I have 12 volts, of course, the other one is automatically determined, so you don't need to waste time. So what I'll do here is put this as 12, and this then will be 6. Observe that the capacitor with a larger capacitance has the smaller voltage, and the capacitance with a smaller capacitor with a smaller capacitance has the larger voltage. This is as it should be, because the charge of the capacitor for 1 microfarad should be the same as the charge on the capacitor with 2 microfarads. The charges have to be the same. You cannot have different charges in a series combination. Because of that neutral metal island shaped like the letter H, if seen sideways, the charges on the two capacitors have to be the same, and that's only possible if a smaller capacitance has a bigger voltage. Let's actually work out the charge here. The charge Q1 is, well, it's already 12 mu C, so I don't have to do any more. It's already there, so never mind. So I'll put 12 here and 12 there. And the last step for this one, I will actually go ahead and find the energy. U sub E equals 1/2, U sub I equals 1/2 Qi times Vi, which means 1/2 circle I, triangle I. So let me do this for all three of these. 1/2 of 18 is 9, and 54 times 9 is 486. Again, something I did beforehand, before this video. Now 6 times 6 is 36, because that's 12 divided by 2. And that is 12 times 12, 144 divided by 2, which is 72. And now is the moment of truth. Is energy conserved in your analysis. So that I'll call that a sanity check. By the way, it's not exactly a check of whether you've done the work right or not, because if you've done everything consistently wrong, you will still pass the sanity check. But still a good thing to check. 480 is 72 plus 36 plus 486 the same or not as 594. You will find that it is the same.